Okay, this is notes 12.1, and it asks, when does a reaction appear to stop? Well, when a reaction is very slow, is very slow. Oops. And that should be reaction is. When a reactant is used up, or when a reaction reaches equilibrium. Now, we should have watched that video, notes 11.6 on Edpuzzle, and the teacher in that video discussed an irreversible reaction. An irreversible reaction is one that you cannot, that only moves in one direction, right? So he used the example of baking a cake. Once you bake a cake, you can't unbake the cake and get back the flour and sugar and eggs. It's done. The reaction's moved in one direction, and that's the end of that. And we call that reaction reversible. So in an irreversible reaction, the reaction proceeds until the reactant runs out. We say it has reached completion. That should say reached. Okay, for example, A turns into B, and that's the end of that. This would be an example would be combustion. Okay, once you blow up that hydrogen, that's all she wrote. Well, actually, that's not true. If you were to, but let's just go ahead and assume it is. Okay, you would have to collect all the water and then run electrolysis through the water. But for the most part, it's going to be real difficult to collect the water vapor. All right, especially the larger the reaction is. So let's just say that once you blow up that once you blow up that hydrogen and you create water vapor, that's it. Okay. However, there's a different class of reactions here, and that's called reversible reactions. In reversible reactions, both directions proceed at the same time. Like this. A forms B, but at the same time now, what's interesting is B goes back and forms some more of A. So they're going back and forth, and these are extremely common. The classic example of this is the dissociation of a weak acid. This is happening in your body constantly. Okay, you've got trillions of different reactions going on at equilibrium. Okay, equilibrium is taking place, and the dissociation of a weak acid is kind of the classic chemistry example that we calculate, not in this class, but in honors chemistry and in AP chemistry. You spend a lot of time calculating the dissociation of a weak acid. Okay, and so let's look and see what this looks like if we put this on a graph. Let's just call it, let's say, the dissociation of weak acid. We can do that, and let's just graph what an equilibrium will look like as a function of time. okay, which is what it is, and I'm going to get into that in a second. If we say time is on our x-axis in seconds, and on our y-axis we have concentration in molarity, big M. Okay, so big M, concentration, molarity, versus time. Let's see what that looks like. When we start a reaction, we have a high concentration of reactants, don't we? Okay, we have reactants. And what happens is, over time, these reactants the concentration starts to decrease. Why? Because they're making products. They're making products. And then it starts to level out, like so. We'll call these reactants A. As we run out of reactants A, because they're making products, it starts to level out. Notice what doesn't happen. It doesn't go in a straight line down this way and go all the way to 0. As I write this out, I want you to think about, why doesn't it go all the way to 0? Okay, so these are reactants. Okay, well, on the flip side of this, when we start our reaction, we don't have any products, do we? Because the reaction hasn't started yet. So our products are at 0, but watch what happens. As we start to make product, the concentration of products increases, and then it starts to level out. It starts to level out. And I want you to think about this now. Why doesn't if you're making new product, why doesn't it just go all the way in a straight line like that and then end? Well, because in an equilibrium, let me write this out here. In an equilibrium, in a reversible reaction rather, these products are forming more reactants. It's going back in the reverse direction. So you're getting, as you're creating these products, at a certain point, these products start to turn around and create more reactants. Okay, so that's why you don't get these straight lines that just go like that. Okay, but rather what you get is a system that levels out. And the point where it levels out, let's just say where it becomes parallel, I'm going to go ahead and just kind of estimate it. Let's just say right there, this is the point of equilibrium. Okay, this is where the rate, now remember this is a rate because we're looking at time here. Okay, this is all happening as a function of time. So that's why it's a rate. This is the rate that levels out. Okay, these rates become, parallel to each other, and that's whenever you have an equilibrium. Okay, that's when you have equilibrium. So equilibrium does not mean equal concentration. Look, it clearly doesn't mean that. Okay, it doesn't mean equal concentration, because your concentration of B is higher than your concentration of A. Okay, so it doesn't mean equal amounts. Equilibrium happens when the forward and reverse reaction takes place at equal rates. Okay, at equal rates. We know a system is at equilibrium when we observe constant observable properties. Constant being the key phrase here. Constant observable properties. Constant being the key phrase. What do I mean by that? Example. Time to get to class. pH is constant. Color change is constant. What else can we say? Conductivity. These are things we measure that will tell us, hey, if we reach a constant number here, we're at equilibrium. It's really big. The big one is pH, though, and we're not going to get into all that in this class, but that's the main one. Hey, listen, it looks like I'm running out of time, so I'm going to do a second video here.